Hello students, I am Vishwajit. Welcome to my YouTube channel Best Physics Guide by Vishwajit. Today I am going to discuss about nucleus radioactivity, that is nuclear physics. You know that a nucleus is formed with mainly two particles, proton and neutron. Proton is the main particles of a nucleus. Proton number of an atom is denoted by P and neutron number of that atom is denoted by small n. An atom may have neutron or may not have neutron. For an example, protium has no neutron inside its nucleus, but proton is the main particle of an atom. That's why the proton decides the chemical property as well as physical property of that element. That's why proton number of an atom is known as atomic number, and it is denoted by capital Z. With the change of the proton number of an atom, the physical as well as chemical property changes. And the mass number is the proton number plus neutron number of an atom is known as mass number. It is denoted by P plus N or Z plus N. Here atomic number can be represented by Z. That's why mass number is equal to Z plus N. Now we can distinguish the atoms into three categories. Isotopes. Some atoms have same proton number. Some atoms have same proton number. That is, their chemical properties are same, but their mass number may be different. That is, the number of neutrons inside the nucleus are different. These type of atoms are known as isotopes. Example, hydrogen atoms has three isotopes: protium, deuterium and tritium. First, protium H11, that is its proton number or atomic number is 1 and mass number is also 1, that is no neutron. Next, deuterium, 1 neutron 1 proton, therefore mass number is 2 and atomic number is 1. Tritium, 1 proton 2 neutrons, that is mass number is 3 and atomic number is 1. Although these are the atoms of hydrogen, but since their mass number are different, that's why their some physical properties also different, but their chemical properties are same. Tritium is mainly radioactive. Next, isobar. What is isobar? When two atoms having same mass number but different atomic number, they are known as isobar. Example, C, that is carbon 14 and nitrogen 14. They have same mass number, that is 14 and 14, but different proton or atomic number. Carbon has 6 protons and neutron has 7 protons in their nucleus respectively. That's why their chemical properties are different. Next, isotope. When two atoms have same Newton number but different atomic number and different mass number, that is same at Newton number but different mass number or atomic number, then they are known as isotone. Isotone, examples of isotones are carbon 14 and oxygen 16. Carbon 14 and oxygen 16. They have same Newton number, that is C14 has 8 Newton numbers and oxygen 16 has 8 Newton numbers. That's why they are isotone. Next, atomic mass unit or AMU. It is equal to 1 by 12 into mass of a C carbon 12 atom. That is C12 atom. 1 by 12 into mass of a C12 atom. You know that mass of 1 mole of C12 atom is 12 gram. Therefore, 1 AMU is equal to 12 by 12 into 6.023 into 10 to the power 23. And 6.02 into 10 to the power 23 is the Avogadro number. And this is equal to, therefore, 1 AMU is equal to 12 into by 12 into 6.023 10 to the power 23 gram. This gives 1.67 into 10 to the power minus 27 kg, or approximately 931 mega electrovolt. 931 mega electrovolt. That is 1 AMU is equal to 931 mega electrovolt. Next, nuclear fission. You know that if we can break the nucleus of a heavy atom, then some huge amount of energy is released due to the change of mass of the parent nucleus and the daughter nucleus. This is known as nuclear fission. Nuclear fission mainly takes place due to the collision between the heavy nucleus and the slow neutron or the thermal neutron. Here uranium 235 is stacked with a slow neutron, and therefore it produces uranium 236, which is very unstable. Then uranium 236 breaks into mainly 3 parts. First part is Ba 141 and Kr 92 and 3 neutrons, and in this process we got 200 mega electrovolt energy. 200 mega electrovolt energy. That is when heavy nucleus, that is uranium 235, is stacked with a slow neutron, then we get beryllium, krypton, one beryllium atom, one krypton atom, 3 neutrons, and approximately 200 mega electrovolt energy. Here the change of mass in this reaction is approximately 0.2153 AMU. And according to Einstein's special theory of relativity, we know that mass can be changed into energy. That's why here this change in mass produces energy. We know that delta E, that is energy produced in this reaction, is equal to delta M, that is change in mass into c square, where c is the velocity of light in vacuum. This is equal to 0.2953 into 931 mega electrovolt. Since 1 AMU is equal to 931 mega electrovolt, this gives approximately 200 mega electrovolt. We can use this Newton, that is product Newton, for another nucleus fission or another nucleus reaction. To produce this, to transfer these newtons into slow newtons, we can use moderator. As graphite, heavy water, they used as moderator, and by this moderator we can transform these newtons into slow neutron or thermal neutron. Next, chain reaction. What is chain reaction? With the reaction of uranium 235 and slow neutron, we get 3 newtons, and these newtons can strike with the other uranium nucleus, and due to the reaction of the second part, this uranium nucleus can produces 3 newtons from each uranium nucleus. That's why this rate of reaction accelerated, and the rate of production of uranium neutron is accelerated. This reaction is known as chain reaction, and this neutron can strike the other uranium nucleus. In this way, we get huge energy, or this is known as chain reaction. And chain reaction has 2 types. One is controlled chain reaction and another is uncontrolled chain reaction. When we can control the rate of reaction, then this is known as controlled chain reaction. It is used in the atomic power supply station or in a nuclear reactor. In a nuclear reactor, we can use the cadmium rod. We use the cadmium rod to change or control the rate of chain reaction. But in case of atom bomb, we do not control the rate of this chain reaction. That's why this is known as uncontrolled chain reaction. We can use the controlled chain reaction for the development purpose of human being or development purpose of our nature. Although the wastage of the nuclear reaction is also radioactive and they are harmful, but if we use or recycle this wastage material, then we can use the nuclear fission or chain reaction for good purpose or development purpose. But in case of atom bomb, we cannot control the rate of nuclear reaction or chain reaction. That's why by an atom bomb we get huge amount of energy which can destroy the vast area. That's why atom bomb is very harmful for our mankind or for our earth. Next, critical mass. The minimum amount of mass of uranium-235 which can occur the chain reaction is known as critical mass. That is, to start chain reaction, we are to got some minimum amount of radioactive or uranium-235 mass which can start chain reaction. Now, the neutron reproduction factor, neutron reproduction factor is known as the number of neutrons produced in one stage of chain reaction divided by number of neutrons produced in the previous stage of that chain reaction. This is known as neutron reproduction factor. In an atom bomb, the nuclear reproduction factor is greater than 2.5. That's why it is uncontrolled chain reaction. But in a nuclear reactor, the neutron reproduction factor is equal to 1 or slightly more than 1. That's why it is a controlled chain reaction. Next, nuclear fusion. This is the opposite process of nuclear fission. Nuclear fission takes place for heavy nucleus, and nuclear fusion takes place for light nucleus. Here, 4 protium moves with huge velocity and strikes with each other and gives helium nucleus or helium atoms and 2 protons and 2 neutrino and 27.5 mega electrovolt. In this case, the change of mass takes place, which change of mass produces energy which is approximately equal to 27.5 mega electrovolt. To start this type of reaction, initially we need huge amount of energy which we can get from nucleus fission. That's why it is said that nuclear fusion follows nuclear fission. Nuclear fusion follows nuclear fission. The main energy source of energy of any star is nuclear fusion. Inside the sun, nuclear fusion takes place. That's why we get huge amount of energy from the sun. We can get nuclear fusion by carbon-nitrogen cycle. Here, initially C12 carbon nucleus strikes with a protium and reacts with protium and gives us nitrogen 13 and gamma ray. Now, nitrogen 13, from nitrogen 13 we get carbon 13 plus 1 positron and neutrino particle. Next, carbon 13 reacts with 1 protium and gives nitrogen 14 plus gamma ray. Next, nitrogen 14 reacts with protium and gives oxygen 15 plus gamma ray. Now from oxygen 15 we get nitrogen 15 plus 1 positron and neutrino particle. Next, from nitrogen 15 reacts with 1 protium and gives carbon 12 plus 1 nucleus of helium. This is known as carbon nitrogen cycle. Therefore, from this reaction we get the 4 and protium reacts with each other and gives us 1 nucleus of helium, 2 positron, 2 neutrino and 27.5 mega electrovolt energy. Here C12 nucleus or carbon nucleus acts as a catalyst. Proton-proton cycle. Actually, this reaction occurs inside the sun. Proton-proton cycle reaction occurs inside the sun. Here, 2 protium reacts and gives us 1 deuterium, 1 positron, neutrino particle and 0.42 mega electrovolt energy. Next, 1 deuterium reacts with 1 protium, gives us helium 3 nucleus, 1 neutrino particle, 5.5 mega electrovolt energy. Next, 1 helium 3 nucleus reacts with another helium 3 nucleus and gives us helium 4 nucleus and 2 protium and 12.8 mega electrovolt energy. Therefore, this cycle gives that 4 protium reacts with each other and gives 1 nucleus of helium, that is helium 4 nucleus, 2 neutrino, 2 positron and 26.7 mega electrovolt energy. That is, from proton-proton cycle we get 26.7 mega electrovolt energy. And this, by nuclear fusion, we can get huge amount of energy, and its main raw material is hydrogen or protium, which can available in our earth, and the wastage material are not very harmful for our environment. That's why from this reaction, that is from nuclear fusion, in future we can get huge amount of energy. But the main problem is the amount of energy. All this, since the amount of energy is huge, therefore we cannot control this type of this amount of energy. That's why this energy is not possible to use for humankind or mankind for present day. But I hope that, or we hope that in future we can use this reaction or proton-proton reaction or nuclear fusion for our development purpose. Next, mass defect. What is mass defect? You know that there is some difference between the actual mass and the theoretical mass of a nucleus. This is known as the mass defect. It is denoted by delta M. Then mass defect delta M is equal to difference between the theoretical mass and the actual mass of a nucleus. Here proton number Z and into MP, where MP is the mass of a single proton and A minus Z is the Newton number inside the nucleus, into Mn, where Mn is the mass of a single neutron. This is the theoretical mass of that nucleus, and capital M is the actual mass of that nucleus, and this difference is known as mass difference or mass defect. Then what is the main reason of mass defect? You know that inside the nucleus, protons and neutrons exist in a very small place. According to Coulomb's, positive proton always repel and the positive another positive charged proton. That's why two same charge or like charge proton should not exist inside the nucleus. But protons can exist inside the nucleus in a small place. Why? Because there is some energy exist inside the nucleus which bounds the nucleons inside the nucleus. This force is known as binding force or nuclear force. This force is known as strong force, which is the strongest force in nature. And there is some energy which bounds the nucleons inside the nucleus. This energy is known as binding energy, and this energy is produced from the mass defect. That is, the difference in the mass of the nucleus converts into binding energy. According to the Einstein's formula, E is equal to mc square. That is, binding energy of the nucleus E is equal to delta m into c square. This is the expression of binding energy. That is, binding energy is equal to z into mp plus a minus z into mn minus m whole into c square. You know that c is the velocity of light in vacuum. Now XX mass. When the actual mass is greater than the theoretical mass of the nucleus, then the difference is known as XX mass. Here XX mass is equal to capital M minus ZMP plus A minus Z into Mn. XX mass of protium is 0.0083 AMM. Mainly XX mass is appeared in case of light atoms, and mass defect is appeared in case of heavy atoms. Okay, in case of heavy atoms, the mass defects is huge, but in case of C12, that is carbon atom having 12 mass number, is mass defect is 0 or XX mass is 0. This graph roughly shows the variation of binding energy per nucleon E by A, that is binding energy per nucleon versus mass number. You know that this graph starts from protium, then deuterium, tritium, helium, after that lithium, C12 carbon, nitrogen 14, oxygen 16, fluorine 19. This graph peaks almost iron. After that it decreases, and at the uranium 235, binding energy per nucleon is very small. This graph shows the stability of the nucleus of an atom. Binding energy when the binding energy per nucleon is more, then the nucleus is more stable, and this peak and these peaks are shown, and these peaks and troughs are shown the more stability of the nucleus of that atom. That is helium lithium, C12 carbon, oxygen 16, nitrogen 14, 19 fluorine are more stable than the other atoms among them. These atoms or the nucleus of these atoms are more stable than the other atoms neighboring them. Here the new binding energy per nucleon of uranium 235 238 is less. That's why they are easily breakable. That's why the heavy nucleus or uranium 235 uranium 235 are radioactive elements, and they can participate in nuclear fission. On the other hand, the light atoms like protium, tritium, they also can participate in nuclear fusion. When the Newton number to proton number, that is n by p ratio of a nucleus, is greater than 1.5, then the nucleus of an atom is radioactive. It spontaneously emits alpha ray, alpha particle, beta particle, and gamma ray. In this way, this nucleus try to decrease the n by p ratio than 1.5. In this way, the nucleus try to be a stable nucleus. The most stable nuclear atom or most heavy atom is lead. That's why the radioactive heavy nucleus try to be transferred into lead atoms. There are three types of radioactive rays. One is alpha. Alpha is mainly the alpha particle, which is the nucleus of helium atom. It is positively charged particle. And beta particle is the similar to the mass and the charge similar to the mass of the electron and charge of the electron. That is, mass of beta particle is 9.1 into 10 to the power minus 31 kg, and charge of beta particle is 1.6 into 10 to the power minus 19 coulomb, minus 1.6 into 10 to the power minus 19 coulomb. And gamma ray is a radioactive wave or electromagnetic wave, or gamma ray is photon particles. When a nucleus emits alpha particle or beta particle, then the energy level of the nucleus is increased. That's why it try to jump to the high energy level to low energy level. That's why in this way the nucleus emits gamma ray. Alpha particle, beta particle, or gamma ray do not emit at the same time. Beta particle may be emit, gamma particle after emitting beta particle or alpha particle, gamma ray may be emitted. But at the same time, alpha and beta particle do not emit. Actually, alpha decay is the spontaneous decay of an radioactive element. When a radioactive element or nucleus has not enough energy to emit alpha particle, then it emits beta particle. Due to the emission of alpha particle, a nucleus loses 2 protons and 2 neutrons. That's why a nucleus, the daughter nucleus has 2 less, but the atomic number is 2 less than 2 than the parent nucleus, and the mass number is less than 4 than the parent nucleus. Let this is the parent nucleus, its mass number is A and proton number is Z. When it emits one alpha particle, that is nucleus of a helium atom, then the daughter nucleus has A minus 4 mass number and Z minus 2 proton numbers. When the parent nucleus emits one beta particle, then the mass number of the daughter nucleus is same, but the proton number is increased by 1, that is Z plus 1. Due to the emission of gamma ray, the proton number and mass number do not change, but the energy level of the nucleus is decreased, that is nucleus jumps from a high energy level to lower energy level. In this way, due to the radioactive decay, the nucleus of the atom changes and the proton number and mass number changes. That's why the daughter nucleus has the different chemical properties of the parent nucleus. Now, law of decay, that is rate of decay of an radioactive element, is directly proportional to the number of radioactive atoms present at that moment in the radioactive reaction. That is dN dt is directly proportional to minus n, where n is the number of radioactive atoms present at that moment in the nuclear reaction, and dN dt denotes the rate of decay. The negative sign denotes the decay, that is in the increase, during the increase of time, the value of n decreases. That's why and minus sign or negative sign is introduced. This gives dN dt is equal to minus lambda into n, where lambda is a proportionality constant known as decay constant. This gives dN dt is equal to minus lambda into dt. Integrating both sides, we have dn by n is equal to minus lambda integration of dt. Lower limit of n is n0, that is the n, where n0 is the initial number of radioactive elements present or radioactive atoms present in the reaction. That is when t is equal to 0, n is equal to n0. When time is t, then the number of radioactive atoms is capital N. By integration, we have ln, that is log e base n by n0 is equal to minus lambda t. This gives capital N is equal to capital N0 e to the power minus lambda t. This is known as the exponential law of radioactive decay. This graph shows the variation of capital M with respect to time. This is the exponential graph at time t is equal to 0, n is equal to n0. After infinite time, the value of n becomes 0. When n by n0 is equal to half, then small t is equal to capital T. Here capital T is known as half-life of the radioactive elements. That is, after capital T time, the number of radioactive atoms becomes half of its initial number. Then capital T is known as half lifetime or half life of that radioactive elements. Since we know n by n0 is equal to e to the power minus lambda t, therefore half is equal to e to the power minus lambda into capital T. Since at t small t is equal to capital T, n by n0 is equal to half. This gives lambda into capital T is equal to ln2. This gives capital T is equal to ln2 by lambda. This is the expression of half-life, or this is the relation between half-life and decay constant of an radioactive element. Now, mean life or average life of the radioactive nucleus, that is T bar is equal to integration 0 to infinity small t into dn whole divided by n0. This is equal to integration 0 to infinity lambda n0 e to the power minus lambda into t into dt by n0. This integration gives 1 by lambda. Therefore, mean life is reciprocal of the decay constant. Now, activity is equal to the rate of disintegration, that is modulus of dn dt is equal to lambda into capital M, or activity is known as rate of disintegration. And units of activity are becquerel, Rutherford, Curie. Becquerel 1 becquerel is equal to 1 dps, that is disintegration per second. 1 becquerel is equal to 1 disintegration per second. 1 Rutherford is equal to 10 to the power 6 dps or disintegration per second. And 1 Curie is equal to 3.7 into 10 to the power 10 disintegration per second. By radioactivity, we can find out the approximate value of the age of the earth. Let N1, capital N1, be the number of uranium atoms present in a uranium mine, and N2 be the number of lead atoms present inside that mine. Now the age of the earth is small t is equal to 1 by lambda ln n1 plus n2 by whole divided by n1. This is the expression of the age of the earth, while lambda is the decay constant of uranium. We can also find out the age of an ancient material by the carbon dating method in this process. And in medical field, radioactive elements are used to treat cancer patient. We can find out the age of a tree by carbon dating method. That's why radioactive elements are very important for our life. So I am going to finish my video for today, and please subscribe my channel, and thank you for watching my video. Have a nice day.